calculus is actually a two-part thing. We're starting with just the first part of it. So it tells us it's defined by functions like this. So where a function is equal to the integral, but you'll notice this one you're integrating from a, which is a constant, up to x, which is a variable. And our function is in terms of t. So it's like the integral from, like an integral from 2 to x of t squared dt. What happens if we deal with that? Alright, so if the function is continuous and on a closed interval, and we're only dealing with an x in that interval, then really we're only going to have to worry about that x, that variable. We will get an actual number answer as long as x is a number itself. In terms of thinking about the graph, we know that an integral gives us area under a curve. So if we are integrating with respect to x, x is somewhere in that, and it's basically the area so far. So you can come up with a formula for what the area is from your starting point up to different points along the interval. You know, if my interval went from 1 to 5, I could get a formula for my area. So if I wanted to go from 1 to 2, or from 1 to 2.5, or 1 to 3, or 1 to 3.5, I'm not integrating 4 or 5 different times. I have a formula for how to find that area. We're going to do our first example just strictly by looking at a graph. So we have this function with this graph. G of x is defined to be the integral from 0 to x, and we are going to estimate all of these values and then draw a picture. So if I say g of 0, g is the integral, so area under a curve. If I'm looking at g of 0, this thing started at 0 and ends at 0. So if I start here and end here, what's my area? 0. We haven't done anything yet. G of 1, so from 0 to 1, what's my area? So kind of use these boxes to estimate. Our area would be this stuff, so what would that be approximately? Probably about 1, don't you think? This little triangle will kind of fill in that one down there so we get a full box. So G of 2. We already know from 0 to 1 it's 1. From 1 to 2, I add in 2 more boxes, so my total area to that point would be 3. G of 3. So from 0 to 2, we're already at 3. From 2 to 3, how much more would we add in? It's going to be more than 1, isn't it? What would we call that? What do you? 1.25? Very precise. Okay. So that would give us a total of 4.25 approximately. Okay. What happens when you add in things under? It subtracts. So how much would I be subtracting off here? Yeah, it's about the same as this, isn't it? So I'm subtracting off 1.25, so that's going to take me back to 3. G of 5. So we're still subtracting off. How much am I subtracting off again? 1.25, so it takes me to 1.75. Does everybody understand how we approximated each of those values? So next, I want you to draw the graph of G. So really, we just have to plot those points. So G of 0 was 0. G of 1 was 1. G of 2 was 3. G of 3 was 4.25. G of 4 is back to 3, wasn't it? And tangent of 5 was 1.75. And then draw in a curve. So that is essentially what the graph of g looks like, the antiderivative. So part 1 of the fundamental theorem of calculus really doesn't tell us anything we don't already know. If a function's continuous, then g, which is defined as the integral, is just the antiderivative. Key things, we have to be continuous and differentiable on that interval. We can't have breaks in our curve, we can't have the sharp corners that keep it from being differentiable, those kinds of things. Okay. So I want to look at this problem. We're going to do two things here. I want to find the derivative of the integral from 3 to x of t squared plus 2t plus 1 dt by the fundamental theorem of calculus and by working it out. So let's work it out first. So I want the derivative of this. So first we would do the integral piece, right? The antiderivative. So the integral would be 1/3 t cubed plus 1/2 times 2 would give me a 1t squared plus t. We are integrating from 3 to x. So if I plug those in, I get 1/3 x cubed plus x squared plus x minus, when you plug in a 3 cubed is 27 times 1/3 is 9. 3 squared is 9 and 3. Okay, then what am I asking you to do with this? We did the integral piece, but I want you to find the derivative of that. So essentially this is my function. So I want you to find the derivative. And what do we get when we do this derivative? Tell me the derivative, guys. You can do that. X squared plus 2x plus 1. Okay. Does that look familiar to you in any way? Where have we seen something similar? Something squared plus 2 times something. Yeah. Isn't it almost identical to that, except my variable changed to an x? A derivative and an integral are opposites of each other, so they should cancel each other out. That's what the fundamental theorem of calculus is telling us. That if I wanted the derivative of this, it is equal to f of x. So it's equal to this original function, but all you have to do is change your variable to an x. So by the fundamental theorem of calculus, if I want the derivative of the integral, I don't have to work anything out. I just take my function, and my variable is now an x. Because a derivative and an integral should cancel each other. Any questions there? So here's our next example. Right, I want the derivative of this function. So we just have to do a couple things to make sure the fundamental theorem works. It has to be a continuous function and it has to be differentiable. So a square root is defined as long as what's underneath is positive. Will 1 plus something squared always be positive? Yes. So I'm just going to make a quick note to show that I talked about that. That means we can do the fundamental theorem of calculus. So what would be the derivative of this? Square root of 1 plus x squared. It has to go from a constant up to x. Has to be continuous and differentiable. And then all you have to do is change your variable. Now, if you were confused, you could actually integrate it and then do the derivative. You get the same thing. This just saves a lot of time. Let's do another one by working it out, because this time I changed it. I am going to x to the 4th. So it's not quite like the fundamental theorem. 2t minus 3, that's a polynomial, so it's continuous and differentiable. I'm starting at a constant, but I didn't stop at x. I stopped at x to the 4th. So let's see what changes when we do that. So if I want to work this out, first I have to integrate. What is the antiderivative of 2t? T squared minus 3t from 1 to x to the 4th. If I plug that in, I get x to the 4th squared minus 3 times x to the 4th minus, if we put in a 1, and this gives me 1 minus 3, which is negative 2, so minus negative 2 makes plus 2. So here's my function. So now I need the derivative of that. Which would be 8x to the 7th minus 12x cubed. Not automatically obvious how that's related. What could I pull out of here? A 4x cubed. That leaves me a 2x to the 4th minus a 3. So do you guys see the shortcut instead of working that all out? Look at our original. We went to x to the 4th, so I replaced the t with an x to the 4th. What's this 4x cubed? The derivative of x to the 4th. It's like a chain rule, essentially. So if you don't go up to just x, if you have some function with an x in it, you're plugging that in for your t's, and then you have to multiply by the derivative of whatever that function would be. So let's do one using that shortcut. D over dx, that just means the derivative of the integral from 1 to x to the 4th of secant t dt. Now secant isn't always defined, it does have asymptotes, but let's just assume I'm talking about a nice interval where we could do the derivative. So if I wanted to do this derivative, I replace my t with x to the 4th, and I take the whole thing times 4x cubed. part 2. This is what we have already been doing for finding our integrals. So we've been calculating the antiderivative and doing the top minus the bottom. Now I'm just telling you that is the second part of the fundamental theorem of calculus. So this we've already been doing, we just didn't have it as a theorem. So nothing new here. So those are the two pieces put together on one slide if you need to look at it. So now let's just keep practicing some of our integrals. The integral from 1 to 3 of e to the x dx. What is the antiderivative of e to the x? So then that's just e to the third minus e to the first, which is just e. Why don't you guys try the next two examples? Just an integral from 0 to 1 of x squared dx. So that would be 1/3 x cubed from 0 to 1. And you should have just gotten 1/3. I saw some problems with the next one. This is the integral from 3 to 6, dx over x, that's like a 1 over x dx. Okay, if you wrote it as x to the negative 1, when you add 1 to that power, you get 0. That should be a big clue right there that that's not right. I saw several of you write your antiderivative as 1. If you do the derivative of 1, do you get 1 over x? No. What has a derivative of 1 over x? Natural log. So that's the natural log of 6 minus the natural log of 3. Okay, what do you remember? If I'm subtracting two logs, how do I put them together? Division, yes. That means the natural log of 6 over 3, or the natural log of 2. Very good. I couldn't help but throwing that in. Okay, let's do a little more complicated one. We've done a lot of antiderivatives before, so let's throw something new in. We've done some basic antiderivatives with absolute values. This one is a little more complex. What did we have to do first when we were working with these? So if I set x cubed minus x equal to 0, I can take out an x. How do I factor x squared minus 1? So this thing equals 0 at 0, negative 1, and positive 1. Okay, negative 1 is one of my endpoints, so we're going to have to integrate from negative 1 to 0, from 0 to 1, and from 1 to 2. If I'm going from negative 1 to 0, if you put like a negative 1/2 in here, is this positive or negative? If I put in a negative 1/2, that would be a negative 1/2 cubed is 1/8 minus negative 1/2, positive. So the absolute value doesn't change it. Okay, if you put in something between 0 and 1, so if I put in a 1/2, 1/2 to the third is 1/8 minus 1/2, that would be negative. So we would have to do a negative x cubed plus x. From 1 to 2, so if I put in 2 didn't make it equal 0, so we could just put in a 2. 2 cubed minus 2, 8 minus 2 is positive, so the absolute value doesn't change it. So now we are ready to integrate all of these. X cubed would go to 1/4 x to the 4th. Antiderivative of x would be a 1/2 x squared. This would be a negative 1/4 x to the 4th plus a 1/2 x squared. So if I plug in a 0, we get 0 minus, if you put in negative 1, you get 1/4 minus 1/2. Put in a 1 for the next one, negative 1/4 plus 1/2 minus, put in 0, you get 0. If I put in a 4, 2 to the 4th is 16 times 1/4 is 4. 2 squared is 4 times 1/2 is 2. Put in a 1, you get 1/4 minus 1/2. 1/4 minus 1/2. That's like 1/4 minus 2/4. So you get negative 1/4. The negative in front makes that a positive 1/4. Negative 1/4 plus 2 over 4 would be a 1 over 4. 4 minus 2 is 2. This would give me a negative 1/4, so the opposite of that would be a positive 1/4. So we get 2 3/4, or you could write that as 2.75, or 11 over 4. Any of those answers are fine. Questions there? Let's just keep going. I want h prime of x if h of x is the integral from 0 to x squared of t cubed sine t dt. So what am I doing here? The derivative of the antiderivative, so this is like the first part of the fundamental theorem. So we know the derivative and the integral essentially cancel each other. What am I going to change my t's to? So we get x squared cubed sine of x squared, and what else do I have to multiply by? 2x, the derivative of the x squared. So if I clean that up, that's an x to the 6th, so it would be 2x to the 7th sine of x squared. Okay, do you want me to stop for the day, or do you want me to finish it? Stop for the day? Okay. So here is the assignment. Tomorrow I will finish the notes. So this is all due on Wednesday. Let me see how much we're ready for. Theoretically, you could probably do all of this at this point. We're just going to keep practicing these tomorrow. So it's up to you how far you go. It's not due until Wednesday.